Differential equations, we're looking at lesson 5.1, day 2, with free undamped motion. A little bit of review. Yesterday, we saw that we could have, for undamped motion for a spring, a second order differential equation of this sort right here. X of t we solved with c1 cosine of omega t plus c2 sine of omega t. By the way, omega squared was k over m, where k was the constant from Hooke's law, and m was the mass of the weight. And here's the thing. When we have this general solution, if c1 and c2, if both of these constants are not both zero at the same, well, if even one of them is not zero, then the actual amplitude is not going to be obvious to us. We solved an initial value problem yesterday. Obviously adding a cosine and a sine wave together, we don't know what the actual amplitude would be right off the bat. But there is a wonderful alternate form that we can arrive at, where x of t would be a sine of inside the omega t plus this Greek letter phi. Phi is the phase angle. And what we're going to see is that a is actually the square root of c1 squared plus c2 squared. Also, in regards to phi, we'd say that the sine of phi would be c1, this constant in front of the cosine of omega t, all over a, and cosine of phi would be c2, this constant, all over a. And we're, of course, going to have a proof for this. This could very well seem unbelievable at this point. But when we're looking at just this regard, where a would be defined to be the square root of c1 squared plus c2 squared, you very well could believe and see, I hope, that you would have the Pythagorean theorem in play. From the Pythagorean theorem, we could see that a squared would equal c1 squared plus c2 squared. And if we wanted to solve for a, we'd take the square root of that. Now, phi would be defined to be such that the sine of phi would be c1 over a. So I'm going to put phi right here. And in this regard, phi would, of course, correspond to this opposite over hypotenuse. Similarly, we could see that then the cosine of phi would be the adjacent over the hypotenuse. And there you have it, a triangle that could be set up. So it's one thing for me to show this triangle right here. It's quite another for me to say that this new form, x of t equals a sine of omega t plus phi, would be equivalent to the form that we saw yesterday. If you're skeptical, that's definitely understandable. Here is the proof, though. As we're looking at this proof, you might remember the sine sum formula. Sine of a plus b would be the sine of angle a cosine of angle b plus, well, then you could have the sine of angle b times the cosine of angle a. I do think when we first learned that in trig, at least I always liked to write it out, of course, as the sine of a cosine of b, and then keeping the same alphabetical order, you'd have the cosine of a, sine of b. Minor change there. You can just see that these two terms here can be switched around. Why are we even looking at this sum formula? Well, that's exactly what we're seeing when we've got omega t plus phi. If we just follow that pattern, we'd have the sine of omega t cosine of phi plus the sine of phi, that's, like your b right here, times the cosine of omega t. But we just saw a moment ago that the cosine of phi is really c2 all over a. We saw that the sine of phi right here was C1 all over A. And then, sure enough, if we were to distribute this A to both, the A's are all going to cancel out. And then you'd be left with C2 sine of omega t plus C1 cosine of omega t. What have we just shown? These two forms are, in fact, equivalent. So, the reason why we're doing this is, once again, you could have an answer like you had yesterday. But again, if we need to find the amplitude, and we could have very good reason to do that, this newer form is the way to go. So let's very quickly jump to our equation that we came up with yesterday. We're not going to have to resolve it. Thank goodness. We're just going to be able to very quickly see that we have a C1. Remember, x was equal to C1 cosine of omega t plus C2 sine of omega t. We came up solving our initial value problem with C1 is 2/3, C2 was negative 1/6. So we'd like to change this to this newer form where we could quickly find out what the amplitude of this wave function is. We could already figure out the period. You can see that that's not nearly as difficult to work out. It's going to be 2 pi over omega, like we saw yesterday. But as we're wrestling with this issue of finding the amplitude, what we can do very quickly is just know that A is equal to the square root of C1 squared plus C2 squared. So we'll get 2/3 squared plus negative 1/6 squared. That's going to get us 4/9 plus 1 over 36. And getting a common denominator, we could multiply by 4 over 4 right here and get 16 over 36 plus 1 over 36. That, of course, continuing over this way is radical 17 up on top. 16 plus 1. A denominator, the square root of 36, that's just a 6. And hey, without very much work at all, you now have A. You actually know what your amplitude is. But let's see if we could actually take it a step further and actually get phi. How do we find phi? Well, as we're wrestling with what we just saw a moment ago, we could see that really we knew that from before the sine of phi was equal to C1 all over A, and the cosine of phi was equal to C2 over A. And you could see that's really what we came up with in our very first definition. A way to remember it is that first constant that we're finding, C1, it's in front of cosine. It actually is matched up with the opposite trig function, the sine function that is. But our C1, of course, is 2/3. So we could say the sine of phi is going to be 2/3 all over this radical 17 over 6. Guys, I just want us to very quickly just notice that it's positive. That's first and foremost. C2, of course, is this negative 1/6 all over this radical 17 over 6. More to the point, cosine of phi is negative. So that then begs the question, in which quadrant would sine of an angle be positive, but the cosine of that angle be negative? Well, we could very quickly go back to our all students take calculus and know that the sine is positive in quadrant 2, where cosine would be negative. This is a second quadrant angle. Now, if we were to go back, actually, to this picture that we saw right here, we could actually come up with one additional very helpful idea, and you could even get it, honestly, from your trig definitions that you see off to the side here. I hope you're also going to know that the tangent of phi would be the opposite all over the adjacent. Now we could have divided the sine of phi over the cosine of phi and gotten C1 over A divided by C2 over A. We would have gotten the same thing. This is a much quicker, easier kind of a setup. And what you can see very fast then is, and we're going to want to do this in radians, we'll have 2/3 all over a -1/6. Now, 2/3 divided by -1/6, we can, of course, reduce and simplify. It would only take a moment to do that. 2/3 is going to get multiplied by this reciprocal of -6 all over 1. And it only takes you a moment to see that really the tangent of phi is going to be -4. But we're going to take our calculator out. We just have to make sure we're in the radian mode. And just double check here. And we are. So I'm going to type in inverse tangent, second tangent of -4. And we'll get -1.326. Now here's the problem. I think we all know that we're looking for a second quadrant angle. But the way inverse tangent is devised, the way it's always worked out, is it can only give angles in the first quadrant and in the fourth. And we've talked a lot about that in the past. So really what you're finding is, inverse tangent is saying that we've got a fourth quadrant angle, a -1.326. So the question, of course, is how do we adjust? Well, this is like our reference angle. You could call it a positive 1.326 reference angle. Or, very cleverly, you could just say, well, hey, how about we just add pi and then we'll go right back in there. So really, that's what phi is ultimately going to be. We're going to add pi to that. That's the same thing as taking pi minus that reference angle if you looked at it that way too. So either way you do it, you're going to be fine. So I'm just going to add a pi. And that's going to be your phi. Your phi is 1.816. 1.816. So, as we're looking at the top of the screen here, we're going to say x is equal to our a, which is radical 17 over 6, sine of 8t plus a 1.816. What's the benefit of this? Well, now we just have one simple trig function to work with. Our periodic motion is described not with two trig functions, but just one. We know the amplitude. It's actually a lot more concise.